let's get back to it. Actually, before we do, let me just check around. Alright, good. Alright, cool. Looks like everything is still working, so off we go. We are working on these switching off of coefficients. So right here, what do I use cell coefficients for? Cell coefficients. Weight putter. Right, I see. So what's going to change here is this is going to become feasible state, cell feasible states, which is something you get by taking feasible states to there, and if not self-finished. Now I can actually eliminate the self-finished array, which is going to be nice. I can just use the count array, or the count which is embedded in the feasible states. So now what will happen is I'm actually going to make a quick little thing so that I can go cell feasible states equals that plus 1, and cell feasible count equals that. Right? And what I do is I say, alright, valid sample count, that's just going to be cell feasible count. End of discussion. So that just goes away. And that's going to make other stuff faster. We're going to take this weight pointer here and we're just going to switch that to weights. Well, it's going to be a little tricky. Yeah, we're getting rid of the weight pointer and we're just going to say right here, we're going to do that and put in the T. We'll clean that up later maybe. Total weight and entropy. Let's see, stride. What is stride? That's for the weight pointer, so we don't need that. Then what we do is we say, alright, T is actually going to be called Ti now. And that is just found by going across the valid sample count. And at each point, we let T equal the cell feasible states at Ti. Alright. So that idea there is just to say, alright, instead of going across a bunch of 1s and 0s and then every time we see a 1, we take the index at that position as the value. Instead we go across 1 to the number of things that are going to be valid, which is a smaller number, less than or equal to the number of total possible things. We don't have an if, and we just have to do this lookup of, alright, if this is the the value at this position, that becomes the T value I care about, and use that to get the weight. So I can't use the strides to go across the weight pointers, which is maybe a problem, but I also am skipping out on an if, I'm skipping out on a bunch of pluses, which is nice. Hopefully that's better. Now it could just be that this memory lookup here that I've added slows things down more than it helps, because now it's going to do a little bit of out of order memory stuff, and then I don't know, we'll have to think about it. It's interesting to think about how you could maybe write code that intentionally reorders the um, the indexes a little bit and therefore gets away from memory uh, locality problems. The other thing I could do is switch this to structure of arrays for the weight, like pull the weight out as a separate array so that I don't have to worry about the fact that there's a large gap between each weight, and then that gets the weights closer. Um, Another thing I could do is store the weight right there in with the t value initially. So lots of options to play with. Now here's where things get interesting. I'm asking, is it actually faster this way? And I do want to keep that note there, but one thing that is true is I know valid sample count before I do anything. So total weight, where does that get used? Only right there, right? Oh, it gets used down here too? We should be able to get total weight for the um, case where sample count is um, yeah, so let's do that. So I'm going to say this we need to do no matter what, and that we need to store there, but this we can wait for that, so now the short circuiting will actually be very helpful. And the only thing we need to change is right here I need to get the total weight, but the good thing is I know the total weight because I know that every sample is available. I can just get that at the beginning, total weight. Right? So let's pop over here real quick. Whoops, what just happened? Alright, right here it's going across the entire sample count. That looks kind of dumb. There we go, that's better. Not sure why I wrote that way. Alright, anyway, so here I'm... Where did I get stride? Up there, huh? Let's put that right there. I'm going to, at each step, in addition to all the stuff I'm currently doing, I'm going to take the total weight plus equal to the weight putter. Okay, and then at the end I can just do total weight equals total weight. So that's nice and good. Alright, cell coefficients. Wait a minute, how do I get the cell coefficients? I roll a die which is best total weight. Right, okay, so best total weight is just going to be correct, and then I can avoid this. I see. I see. Yeah. This is dumb. I wrote this the wrong way. That could look more like this. So the cell coefficient, if it exists, I decrease the die rule. Die rule is less than 0. Element equals T break. Weight putter. Why did I decide not to do a less than there? I guess 0 is a possible outcome, and so I'm saying give that to the next guy. Yeah, okay, makes sense. Weight putter, always increasing the weight putter. That's going to get eliminated soon anyway, but I just want to make sure that that is in an order that makes sense to me. Okay, so doop, doop. Right, so this is another example of going from there to there by TIs, and then letting T equal the cell feasible states, Ti, and then using that to get the entropy sum. Just in here considering whether or not I want to merge these two for loops or not. Thinking about the locality of all these things. The thing right now is that weight by log weight is organized in a way where the weights are more densely packed to each other than they are up here. So I want to kind of get in there and try to fine-tune, time that, and see if we waste a lot of time in this particular section, but not right now. We'll get back to that later. Alright, so here we are. Feasible states. That should be cell stride. Feasible states. Yeah, those are all using the cell feasible states. So up here, I want to grab that again. Except now we're using best x, best y. But everything else is the same. We end up with cell feasible states base, which gives me cell feasible states and cell feasible count. Best total weight times that gives me a die roll. There won't be any weight putter. There won't be any stride. I do need a hit element. I'm going to use ti across all of the valid sample count, and then there doesn't need to be an if. Doesn't need to be a way to put our stride. Ti, which gives me a t. Feasible cell feasible states ti. Take that minus t. Wait. Die roll becomes less than 0, then t is the hit. So that is faster for sure. Alright, coefficients. Yes, so what we need here is to use the cell stride, and we need to grab from the feasible states to grab cell 1 and cell 2. We'll call that cell 1 base and cell 2 base. Doop-de-doo. Alright, so now what's going to happen is we have T2I going across all these guys, and T1I going across all these guys. This was the original thing I wanted to clear up. So instead of having those ifs, what we're going to have is uint32 T2 equals cell 2 T2I and T1 equals cell 1 T1I, and then we can take out these ifs because they're not necessary anymore. There we go. Now what we need is valid sample count 2, valid sample count 1. The way we can get those is up here. uint32 valid sample count 2 equals cell 2 base and cell 1 base, and cell 1 equals cell 1 base plus 1, cell 2 equals cell 2 base plus 1. Alright, so here we are, using the coefficients to print out the results. Right, and what we actually want to do now, this is going to be faster again because we don't have to loop across it to find the right cell to output stuff to. So instead we're going to do feasible states, cell stride, that gives me the cell base. I can then do uint32 32t cell is cell base plus 1, and then this is just cell 0. So don't need that. So this here is going to be feasible states, and we need to go up to get debug output. Feasible states, get debug output. Feasible states, get debug output. Okay, good. And then for each of these, what I'm really doing is I'm going, here's feasible states, here is cell stride, uint32t, the cell is cell base plus 1, here is the cell base, and then t is cell bracket 0. Now instead of cell finished, what I should do is say blah don't need you, if cell base equals 1, then we're finished. So cell equals cell base plus 1. Uh-oh, what was that? No, you didn't. You just have a bug. That's okay, though. I'm gonna debug it. Wait a minute. What's that? Ah, that's Milton running. Alright, bye-bye, Milton. Run it. Oh, I know what's happening here. I haven't done the elimination rule yet. So, 533. Here I'm eliminating cells, but I'm not doing it correctly. So, yeah, this right here is wrong. I can't just set T2 to 0 and call that a day. That doesn't fix anything. What I actually need to do is if these cannot coexist, then I'm altering cell 2. So what I want to do is say, alright, cell 2 T2I equals cell 2 valid sample count 2 minus 1. Right? I say cell 2 is changed. And I also want to set a couple other changes in motion. I want to set the valid sample count 2 to be decreased by 1. I want to set cell 2 base to equal the new valid sample count, because that's where it gets stored long term. And why don't I just stop storing locals and let the compiler make that kind of decision? when it's going to lead to these kinds of confusing situations. Okay, so I decrease the count by 1. What is that? Potential state count. Don't need that. Cell 2 base. There we go. Alright, so alright. Alright, so I move that to there, then I decrease. Right, and this actually this now. So really what happens is I decrease this by 1, and then I use it as the index into cell 2, and I move that to T2i, and then I decrease T2i by 1 so that it starts again from there. That just runs successfully. Can't tell. That looks reasonable to me. Still doing that shape like it's always been doing. Yeah. Yep. The reason it comes out different now is because when it does the observation step, which is what sort of the randomness comes from, that step is still, since it's making different decisions on the roll now because the samples are stored in different order as things go. It's still equally random, it's just given the same pseudo-random like seed, it doesn't end up in the same spot, is all. Alright, so that that satisfies me though. Hey, that looks really neat. Look at this. Look at this. So cool. Awesome. Okay. Next, I would like to switch back to timing and compare the results. So the number of comparisons has gone up. The number of like changes that it is dealing with has gone up. Let's take a look. Actually, let's do it this way. Here we go. Here's with feasible states. There we go. That was the run again command. We can see here, not really a major change. The number of changes has actually gone up, which is, I think, just random. I think that's just, I could change the random seed again and get a different result. Run 10 times for me, buddy. That's getting consistently around 9,000. Oh, there it went to 7,000, 6,000. I don't know. Yeah, it's just random. So the fact that I got 8,101 on that other one might just be random. If I switch to this, what do I get? There's an 8,000. Yeah, maybe it's higher, but I don't know. I don't have enough information about the way it used to be. I do have, however, that the average looks better, because here I had an average of 400, and here I have an average of 350. Although I think there was another time where the average was around this size, so maybe it's no different at all. I also know that this is about the same as that. So it's hard to say. What I'll do is I'll quickly run this way so that I can get more information all at once. Something broken with that. It should have been able to give that to me a piece at a time. Now let me come over here, and I want to. I wish I knew Git better, but I'm going to store right now feasible states method. Then I want to try to restore the code from the previous commit. Git restore previous commit all files. Got it. So I need to run my git log system. Hey, what was that? Why didn't you show me the git log? Great, now I'm totally screwed. Okay, well, let me write these down real quick. So the feasible states, well, I can just put these in here. Git, let's see, that is 7C0A1D and this, if I get on this, I get BA052D5A67. Ah, that's why. Okay. I was confused for a moment there because it looked to me like this was shorter than this because they didn't line up with the semicolon, but I thought I'd counted out the same number of characters in my head, and I was looking back and forth like, the lines up here, why not there? Well, they do line up here, just the semicolons don't line up, or the colons don't line up is the difference. Alright. So, given that, now I have the fun situation where you can't get out of git log because I don't understand and it's busted and stupid. So, let's see, end. end, delete, home, page down, delete, insert in the page up, what about still busted, and so you close that, and you get a new one. No, like a new not administrator one. There we go. Well, not for ed. I don't need a new for coder. All I need is git restore, no, git checkout, 0D1, wait, that's just the one from over there. The one I want to check out is 7C0A1DEEE. Alright, let's pop back over here. Reload that. Rebuild that. Coefficients are back. And now I'll run it again. Multiple times. Hey, first of all, I didn't mean for you to restore all of that. I want you to still run 10 times so that I can get more results. Now run for me. Alright, so hopefully that will return soon and I can get more information on how this one is behaving. Looks like it failed at one point. I'll have to take a look at that. Okay, so doop, doopy doop. Alright, let's take a look. So this, first of all, yep, this looks like a failure to single change. Yeah, these two failed because they are it ended prematurely. The contradictive state, where did it occur? Where do you think a contradiction happened? Doesn't say. There should be X's for the contradiction, but I don't see them. Oh, there they are. Is that a contradiction? If you put a 0 there, it doesn't know what to do with this spot right here. Interesting. Well, let's just delete that particular run of the generator, and we'll just operate with the other 9. Alright, so taking a quick look, we got a count of 8,000, 8,000, 9,000, 7,000, 9,000, 10,000, 9,000, wait. Okay, so this is where it does the change. Let me mark this. I'll just truncate it to right there. Okay, so there we go. So let's see, something like 8,000, 9,000, 9,000, 10,000, 9,000, 7,000, 9,000, 8,000, 8,000, yeah, but it doesn't convince me that it's particularly different from before. Let's see, the single change is what I want to look at here. That's around 400,000. Single change average 400,000, 430,000, 397,000, 397,000. Yeah, 391,000, 400,000, 394,000, 398,000. So these are all around 400,000. All of these 350,000, 350,000, 358,000. That seems distinctly faster in the average right there. Generator runtime. What about those? 348, 3. I bet it won't be hugely noticeable, would it? Let's see. 4, 39, 37, 37. Let's do it this way. Generator runtime. So we have 33, 37, 40, 30, 37, 39, 37, 37, 37. 34, 37, 35, 33, 33, 31, 35, 32, 36, 34. And yeah, they're all in the same order. Single change seems just slightly faster, maybe. 32, 35, 38, 29, 35. Oh, that's smaller. 0, 5, 3, 6. Okay, that doesn't make any sense. How can the total be that small if the average and the count are so much bigger than usual? It's like a weird anomaly level weirdness there. I don't feel like thinking about 3.5, some kind of bug, or I don't know, something. That's a weirdly low propagation time. Like, that average propagation time is larger than the propagation time. Yeah, it's not this one where the failure happened either. Oops. Got the wrong generator time here. Wait, what? Propagation. Not sure how it turns out that it thinks propagation is so small. Is that... Oh, that 4 doesn't line up with that 3? No, it does. It does. That 1 is bigger than that 9, too. Yeah. This many objects with an average of this... Like, this many changes propagated with an average of this much should be much larger than this total. Right? 1, 2, 3, 4 digits. 1, 2, 3, 4 digits. Yeah, if you did that divided by that, you would end up with mystery, mystery, mystery. Does that other one add up? 20605477 times 211. That doesn't add up either. 52788,416 divided by 211. These averages don't make any sense. Okay, that one makes sense. Two, four, 8, 7, 2, 1, 7, 8, 9 divided by 2 and 2. Yeah, that adds up. What about the other ones? 3523010,587 divided by 9008. 391097. Yeah, so something went wrong on this particular one right here. The counts got all messy. Run it again. There we go. Alright, so that's got the same count as before and the same average, but somehow last time it screwed up this number here. Which is crazy. Don't know what that was all about. It's still screwing up the generator runtime. Generator runtime can't be 1/9, can't be that small when this is that big. This one right here makes sense. You got a 2 there, you got a 3, 5 there, you end up with a 3, 7 there. It adds up. What's up with this one getting all funky weird on me? Alright, notice I'll check this out later. It's very interesting. I can just run that random seed and see what's going on there. But eliminating that and getting back on track, how much time we spend on a single change is what I want to look at. Those were all like 3 5s and 3 6s for the most part, with the exception of a 3 0 and a guess not a 3 0, just a 2 9. I thought there was a 3 0 around there somewhere too, but I'm wrong. It's just that 1 2 9 that was low. 3 3 3 6 3 4 3 2 3 2 3 1 3 3 3 1 3 6 3 3. Okay. It looks to me like it's better. 10,068. Although it also looks to me like the average count goes up because of this somehow. The feasible states version. The number of changes you propagate somehow gets larger. Not sure why that would be. Well, anyway, I would like to now git checkout head. Boop, 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 feasible. What the hell? Git checkout feasible. Git checkout BA052D5A67. I don't even know why. Git stash. Awesome. All right. Boop, 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 boop. Feasible states are back. All right. And using feasible states, we got a few advantages, and it looks like potentially a small win. Generator runtime. But not a huge one. So what else can I do? I could, for each cell, keep the total weight in a separate array, or even inside that as another cell of that big array, and then all I have to do is to get the total weight, I could keep an entropy sum and a total weight at all times, and only when that would be nice, because then I don't have to sum these things up every time I'm iterating across them. I just look at what is your current valid sample count. That tells me this. If I see a 0, I've got a problem there. If I see a 1, I think this should just be an assert now, by the way. Alright, let's try it. So I'm going to do let's take a look at well, what I should really do is first boil down more information about what's taking me the most time. So I know that observation is cheaper than anything else. Let me spend a little more time um, uh, looking at propagation. All right, so during a change, um, we uh, we spend a lot of time doing a lot of stuff. What can I simplify? The coexist check. Now, one thing we could be doing here that was done in the original that I thought was probably a good idea that I just haven't done yet is they pre-computed all the coexist checks. So you can see right here the way a coexist check works is um, you pick you pick some pair of cells that you're going to compare. That gives you an original cell that you're centered at and a delta x delta y to the other cell. Then what you do is you grab cell 1 and cell 2, cell 1 being um, the one you're centered at, and cell 2 being the one that you have a delta to, and use the deltas to find a min and max here. So every time I want to compare cells, the first thing I do is I pick which cells I'm comparing, and I get the amount of overlap range in between those two cells. And then we look at the cost of, we look at each sample for cell 2, we look at each sample for cell 1, and we say, let's see if these things can coexist. Now we already know the delta x, the delta y, sample 1 and sample 2. That's the entire amount of information it takes to know whether or not these things can overlap or not. So then we go ahead and run the check here. But the idea is, why not make a four-dimensional lookup table where you have every possible delta x, every possible delta y, every possible sample pair, and given that information, you get out, input that information, and you output the yes or no answer. Can these two samples coexist? Which makes the process of checking these things much, much quicker. So let's take a look at possibly doing that. Because right now I'm spending time on each propagation step in this loop here, which is about 6 net layers deep of nesting. And if I could turn this loop here into just yes/no checker, that would speed things up considerably. At least in this range of code here, it would speed things up. I don't know if it would speed the whole thing up. I guess we could ask how much time do we spend in there, which would be a good thing to do. So let's do that. Single change. How much of our time do we spend in a coexist check? Single change. If we spend a lot of time during a coexist check, or at least the amount of time we spend during the coexist check is a large part of the amount of time we spend doing a single change, then we know that that's a winner and that reducing it will be helpful. Uh-oh. Coexist check. Coexist check begin. Oh. End time counter. Alright, so the amount of time we spent in the coexist check code is magically longer than the amount of time we spent in single change and in propagation and in the entire generator, which is crazy. But it also says that we're just doing a shit ton of coexist checks, and that each one of them is actually very short. That seems to me hard to believe. Let me double check that result. Coexist check. Alright, well, we are doing a bunch of them, a gigantic number of them, and we are spending only a few hundred cycles on them, on each one of them. So getting that down would be great because there's so many of them, even if you get it down by just a little bit. But also, can we get it down? I mean, that's so short. That's already so fast that I'm not sure I'm convinced that looking it up in a lookup table is faster. Like this little, the amount of time between here and here is so short that I'm not really convinced that we can make it much shorter. Let's just suppose, let's run the experiment that there's no time spent here, so that the result is always that they always can coexist. And that we spend no time actually doing any checking at all. Obviously that wouldn't be the case. We would spend some time looking up the sample pair in the table we're looking at, but what would that look like? Uh-oh. What went wrong there? Ah. Display time counter. If C start count does not equal equals 0 and end count equals 0, then what I would like for you to do is what would I like you to do? I would like for you to do something for me, please. Please do the thing where you say printf not hit. No hits. Oh no. Ah, I see. That should be an else if. And it needs a new line character. There we go. So, in that situation, oh well, that's not really a valid test, is it? Because we don't, since we never have any propagation to do in that case. Okay, so let me go back down there, coexist check, and we'll just say things can coexist if t1 plus t2 is less than or equal to 3, then coexist check result equals 1. See if that does us any good. Still getting the same. Oh, that's still 1. There we go. How can all of these have contradictive states? I don't get it. Okay, so clearly cheating the system is not as easy as I imagined it would be. Now what? Alright, I give up. I'm not going to try to cheat it. There's only one way to find out. We're going to have to actually go in there and try it. I'm still saying the average is 141. That's a huge number of checks. Is there any way... Why is it checked so many times? Because every time it does a change, the number of checks it does is the number of neighbors, which is 24 minus, yeah, 24, and for each of those neighbors, 24 times the number of states the current cell has times the number of states the neighbor has, which is as large as sample size squared, and decreases slowly. So you end up with how many samples we have was like 1,000 or something. Well, let me take a look. Let's see if I get a near approximation of the right number of samples. So we have 1, 4, 4, 8, 3, 7, 8 is the number of checks we do, coexistence checks. Now divide that by the number of changes there are, because each of those triggers some of them. So one change does about 4,000 coexistence checks. And the reason for that is it has 24 neighbors. So given any pair of neighbors, it does about 183 checks. The reason it does 183 checks is because each of those neighbors has to go through each pair of states that are available to those neighbors. That's kind of a lot of work. How could we simplify that? Wait, why is that so fast all of a sudden? I haven't changed anything yet, have I? I don't remember changing anything important. Why is that a 1? Holy crap, yeah. It's totally different. It's like half. The count is still the same, but look how low the average is. What did I change? Um, that's interesting. Um, .c. Yeah. Yeah. I messed with all this. Didn't find anything that worked. You're gonna take out the stuff I did for no hits, but that doesn't matter. Right there, what am I doing? I'm just adding in a time checker. Here I'm adding in the time displayer for the time to... There I'm changing that to an assert. What did I do before that? Took out that comment, and nothing else. I didn't change anything. It's just my my new timings are totally different than my old timing. Man, that's weird. Maybe I didn't actually run these correctly or something. I don't know. Okay, well, let me do something. Because it looks like I have better times now for this, for reasons I can't understand, except that maybe I didn't time them correctly the first time around or something. Um, Wait, shit, that's not... This is consistently faster than the other one, it would seem. And this is just switching off of the coefficients into the feasible state array. It's somewhere between 2/3 and 1/2 the time of the other one. Although technically what I should do is go back and run that again too, because who knows what's going on here. Did OBS crash? No, still working. Yeah. Not sure I understand, but I should move on. So that's faster now, which is cool. And now let me go back to considering what to do next. So looking at just one of these runs, it's at this length of time. The breakdown here, as we can see, is that really the reason it takes a long time to do anything is there's just a gigantic number of coexist checks. There's more coexist checks. No, the average number of cycles in a single change is less than the number of coexist checks there are total. But if you were to do the division there, that would make sense, right? So if I do the total number of coexist checks divided by that gives me about 4,000 coexist checks per change. How can I get that smaller? I have one change, I gotta look at all the neighbors and tell it, hey, I've changed, and then I tell all the neighbors to loop through all their states and see if that that change of mine affects them. And they do that by looking at and seeing basically where can I still overlap with remaining states. Now maybe there's a couple ideas here. One thing I could do is say, alright, to speed up the change process, if after a change a cell only has one state left, let's make a grid where we write down, okay, this state says it's got to be like this exactly, and that would allow you to sort of have all of the cells. Oh, you know what you could do is a single change, you could break that up into a bunch of small jobs and run them in parallel. That's for sure. Because you're only changing each cell independently, they're not checking anybody but the center against themselves. So it would be fairly isolated work for each of those cells to check their own problems, and then they just have to push that back out. Like each of them have to decide at the end, oh, I need to change or I don't, and then that has to get pushed into the queue in a synchronous way. But that does give us kind of like 24 jobs that you know can run in parallel if we want to speed it up that way. Another way to think about this though is um, we could store what kind of change happened, like, oh, I deleted these states, like have a list of states. We have a list of states right now that are viable. We could then, after that, have a list of states that have just been removed since the last change, right? And that second list of states, you could look through that and go, okay, maybe have a way to undo the, like to go, okay, after removing this, what has changed, right? That might be a way to think about it. Another way to think about it might be to say, what we're trying to do here is say, given a particular state of, basically, we have the spot where the change happened, right? Super bad at drawing boxes. Here we go. Here we go. Here we go. Here we go. It's a little 5x5 area here. At least for 3x3 boxes, but we could generalize this to larger squares too. And the idea is if a change happened here, all of these guys have to update, because for instance, if he has decided his what state he's going to take, then this entire box here, let me switch to a new color. This entire box here now has fixed values that all cells have to adhere by. And that means that this is the set of squares, like this is the set of cells that have to respond to that. Because, for instance, up here, if I was this cell here, whoops, come on now. That cell there cares about everything going on right here, right? So you can see there's one spot of overlap there. But maybe what I actually want to do is say, because sometimes what happens is this cell right here decided I just got observed and I'm narrowed all the way down to one possible value, and all my neighbors now need to make sure that the only states they're considering are compatible with that. But after that stage of propagation, he might do some elimination. He doesn't eliminate all of his possible states, but he eliminates a few, and then his own neighbors have to respond to that, except now this guy has more than one possible state. So it's like, alright, at this position I'm either going to take on value 0 or value 1. This guy over here decided he was taking on value 3, and the only samples I can see that have a corner opposite of 3 are 0s and 1s. So 2s and 3s are now out for this, and everyone who thought I might be a 2 or 3 needs to eliminate that sample from the set of possibilities, right? What we could do is maybe we can avoid having to do a nested loop of all the samples of this cell and all the samples of this cell compared to each other. Instead, we say, alright, this is the one that changed. Do some kind of pre-processing on the set of possible remaining possible values. And then for each cell, we go, alright, go through all your samples. We've already pre-processed this guy's samples, so we do O of n work for his samples, then we do O of n work for his samples, but we don't do them nested with each other to make it an n squared situation, right? We just do his samples to make this pre-processed thing, and then we do his samples to check against the pre-processed result. And what that might look like is we have a sort of a testing grid that we've set aside that says, alright, we want to know which possible values, how many possible values there are, which there's normally like 2 or 3, there could be 10 or 20, but there's not going to be more than a few hundred, so it's not a crazy large number. And for each of those we make a little grid that's the size of a sample, and we say, alright, put 1s and 0s in these grids, and put a 1 wherever, like if you're in the fourth grid, position 0, 0, if that is a viable value there, right? If 4 is a viable value at 0, 0, put a 1 there. And then what we can do is have, when we're testing this cell, we go across all its samples and we go, alright, for each of these samples, go across its entire overlap region. Now I have the overlap region set to be rather small, but let me make a different example where the overlap region is bigger now. Go across the entire overlap region, which is now these 4 cells here, right? And for each of those spots, look at the for each possible sample that we put at this location, look at what value you would put here and check, is there a 1 in that table on the preprocessed version, right? So the size of the preprocessed version would be n, which is the number of samples, times the size of a sample in memory, and the time it takes to fill that would be well, you could it would be clear the whole thing to 0 and then iterate across all the cells of this guy here, all the possible samples remaining for this guy here, and put in 1s where appropriate, right? And so that's not something you want to store per cell forever, but you could do it like when you begin a change, alright, clear all these tables to 0, iterate his possible states, put in the 1s, then for all the neighbors, iterate their states, and check against that table. Now what you've done is, instead of having to do the n-squared check of every possible sample, every possible state for him versus every possible state for him, at the same time, you've turned that into 2 O of n things that you run in sequence, right? And I feel like that would probably be a lot faster, because that will decrease the number. That totally changes the game of coexistence checking entirely, basically, right? You're no longer coexistence checking by looking at, for every possible sample here, look at all the samples here. You're doing, for every possible sample here, check the overlap once, and then you either know or you don't know. Like, you either know or you know the answer by the end of that, right? You just check all 4 of those once. So you get basically 1 coexistence check per neighbor, per sample that neighbor could potentially, per state that cell could possibly take on, which is however many samples there are, instead of however many samples there are squared. I feel like it could be good. I feel like that could be good. I'd like to try it and see what result we get. So let's dive in there and try that out. So to make that work, I'm going to need more memory during the generate output situation. Now, it's got a certain amount of scratch memory. The scratch memory size is just arbitrary, right? Okay, so generate output. Scratch. What do we do with scratch memory? Scratch start, scratch putter, scratch end, scratch putter. That's where we make the on change queue. Then we move the scratch putter forward. We make the cell finished queue array. Scratch putter moves forward. Scratch putter. We make the change queue. We make the, what is this? N32 position. There we're doing a round to 4 kind of thing. Let me make that into a quick little helper so I don't get confused by that again in the future. Whoops. Round putter, putter, unit 32 boundary, return putter, uint32 from the putter, do minus minus on the boundary. How do you spell boundary? Has it got an A in it or not? Boundary. It's got an A in it. Boundary. Boundary. Position plus boundary. Boundary. Oops. I bumped the thingy do. And then set putter by taking the position, right? Does that agree with me? Cool. And then we can do scratch putter equals that applied to the round putter function on the scratch putter 4. Alright. And then I want to do one more thing, which is I want to take uint8t coexist tables, and that will be why are all of these casting to uint8t? I guess that's just because I don't know if I'm going to change its type in the future, right? So cast that to scratch putter. Uint32 coexist table table size, or coexist stride, or coexist cell stride would be sample width times sample height. This is another example of something you can't do if you have differing sample sizes, or at least it's more complicated because you need the rectangular union for your array then. Right? You need some kind of overarching sample size thing in which all samples can fit. Alright, and then so that's the cell stride. That's how many bytes you want for each cell. And then coexist tables size is going to be the coexist cell stride times the cell count. And then we can memset cell finish, memset coexist tables to 0 on the coexist tables size, and scratch putter plus equals coexist tables size. There we go. So that is just me allocating a little memory out of my scratch buffer so I can set up these tables that we're trying out. At the end of that, I'd like to say if scratch putter, if defined debugging and if scratch putter is greater than scratch end, then go ahead and dereference an int putter to 0 that I try to set to the hexadecimal equivalent of my name, representation of my name, whatever you want to say, however you want to say what these special magic numbers are called, where you make them look like words, and that right there is a bug, because right is landing me there, but left is landing me all the way over there. Definitely a bug. That's weird. Kelly, I never saw that before. Okay, well, fix that later. Hexnav bug. Did I spell debugging wrong? Okay, it's got 2 G's. That seems weird to me right now. Alright, so now, down here where the coexist stuff happens, what I'd like to do is say doopy doopy doo. Let's take cell 1. Alright, first let's build out. We know what change we're building on, so let's just get this right here. First, I memset the entire coexist tables to 0. Then I need to grab cell 1 information. So there's some cell 1 information, cell 1. Here's some cell 1 information. For T1I equals 0, T1I is less than cell 1 base, which is the number of, remember that's the number of valid samples for this cell. We then want to loop over something that looks kind of like this. And we want to say, okay, sample width, sample height. Great. Now let's see, I also want to grab the sample that I care about. So let me grab that right here, sample 1, and let's see, here's how I index into that. And I'm going to say int 32v for value equals that, right? So that tells me the value I want. Then what I do is I go, okay, so the coexist table that I care about is coexist table, by the way. What type did I give that? uint8, good. Coexist table that I care about is from the coexist tables, where you go to v coexist tables. Did I do sample width times sample height times cell count? That's wrong. What I care about is like number of or highest value, right? So that doesn't exist yet, but that's fine. Let me just pull that out as a thing up here actually right away. Later on we'll highest. We'll have to actually write the code that gets the highest value, because we weren't doing that anything like that before, but now we are. Coexist tables. Alright, so mem set that to 0. Pull out the cell. Tell the cell to iterate. For each iterate across its possible sample values. For each of those possible sample values, pull out the sample data, iterate across the entire sample, pulling out the value at each spot. Then what we do is we take v times the coexist table stride, coexist cell stride, no, that should be coexist value stride, cell stride. For each value, we take a width and a height. We take a width times height grid. That's the idea. Coexist value stride. Alright. So, out of water. So I grab the coexist table that I care about, and then I increment or I index into that table, coexist table, using this right here, and I set that to 1, right? So the idea is I'm taking out a v from here, which is from the sample, and I'm using that to pick which table I care about, and then going to the same position in that table and setting that to 1. When I'm done, what I have is a bunch of tables that have 1s wherever a value could show up in that location. Okay? So that'll take some time to fill that table. But once it's filled, what it means we can do is now we iterate across these deltas, and that gives us all of the for each of those, we compute that. That gives us a cell 2. We grab cell 2 information. Then we iterate across the samples of cell 2, like so, each time grabbing its T2 like that. By the way, we should probably grab the T1s like that. Right? Alright, so then what we want to do is we want to answer the question, can this sample, T2, coexist with the T1 cell in one of its possible states, right? In one of its possible configurations. Now that I'm about to do this, I realize this isn't quite right. This is a little different than what existed before, because now it's possible for it's possible that you look at a sample of T2, and it doesn't actually coexist with any of the samples of T1, but it does, each cell of T2 coexists with one of the cells of T1. Now the question is, if I don't propagate it perfectly, is that going to hurt me too much, or will it give me basically the same results? Because what's going to happen is I'm going to have a sample laying around that can't actually ever occur. And I could have discovered it couldn't occur, but I didn't bother checking. So the only way I could find out that it doesn't occur is to do the full n-squared comparison. So I have to either risk having more contradictions as these things get chosen that shouldn't be, or maybe it won't happen. Like, maybe it'll still get eliminated eventually later. And so what we're doing is just sort of imperfectly estimating the way the other one works, but reducing the order of time by a factor of n. So let's try this and see if it remains high quality, and if it does, is it faster? So the idea is I iterate across the samples of cell 2, the possible states of cell 2, and I say for each one of them, can it coexist? And the way I find out is I run a coexistence check. But running a coexistence check does not look like this anymore. Running a coexistence check is just a matter of going, alright, give me sample 2, grab the value of sample 2 at that location, right? And then say, okay, well, go to the pre-processed version of cell 1 and ask, does this cell fit here, right? So I grab out sample 2, V, which is blah 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 blah. Go to the correct coexistence table. To get that, same as right here, you just go to the big coexistence table, index in at the coexist value stride times V, the value you care about. That gives you one coexist table. And then what you want to do is you want to say, alright, at the coexist table, if the coexist table at that location equals 1, equals 0, how does this work? Yeah, then you can't coexist here, right? So then you go boom, go to finish coexist check there, and you're done, right? So you got this pre-processed thing that roughly estimates kind of how the check used to work, and then you can go and get the new sample, check it against this pre-processed thing, and see does this probably work, right? And you get the same result. You're still checking every sample in T2. So for each one you could possibly eliminate it, and if you eliminate it here, we know that it doesn't coexist. It's just that certain things that might be impossible might still stay there, where the other one was absolutely certain that it used 100% of the information available to it. So now the problem is this highest value thing doesn't exist. But that we can fix. To do that, what we have to do is when samples are coming in, we have to iterate across the sample and check it. So uint32 sample size equals samples. Now samples, I ask you, that's a width times height situation. Okay, and let's see. If theta I is greater than samples max value, samples max value equals theta I. Not so hard. That does slow us down a little bit at the head end, but we have plenty of time there. So let me throw in a uint32 max value there. And there, so sample count equals, yes, state sample count will just equal the samples, sorry, the max value will equal the samples max value, right? Uh-oh. Yeah, that's leading to contradictions now. I wonder if that's a bug though, because it's happening right away, which doesn't really make any sense. So, let's take a quick look. Failed equals 1. Yeah, this looks like it's failing right away, so I'm not believing that that's actually a flaw with this method. Not necessarily. There could still be a flaw, but that's not what this is, I don't think. So we look at each of these, and by the way, did we already fill out, yeah, we already filled out the coexist tables, so let's take a quick look at cell 1 base is just 1, and cell 1 says 38. So we just grabbed T1 equals 38 and we filled in all those tables. So I want to see them real quick. What is the highest value, by the way? Let's start with state max value. Max value is 1. So there's, oh, alright. I'd like to see this process. So we picked 38, good. We got 38. We grab that sample and we go ahead and iterate across and go, what value we got here? 1. Alright, we get that coexist table. And we have basically coexist tables, right? And then we have coexist tables plus 9. Both of these should show me 9 at a time. They're both clearly 0 right now. Then I go ahead and start filling in. 9 spots are going to get a 1 on them. So that guy got a 1, that guy got a 1, that guy got a 1, and you can see what's going to happen is each XY position gets a single 1 from this particular sample. So there we go. And since there's only 2 possible values, these are basically bit complements of each other. When there's more samples, what'll happen is there'll be more 1s than 0s probably, because you'll have like, alright, we have one sample that looks like this, and then we have the flip version that fills everything up with lots of 1s. So this might not work. We'll see. What we could do is say that something like this works for stuff that only overlaps at one spot, right? If it only overlaps at 1 or 2 spots, you do this, and if it overlaps at a lot of spots, you do a deeper check against more stuff, right? You do the n squared check if you have like 3 or more overlapping spots, maybe. Or if you wanted to make it exactly the same rule as before, you have it over. You have the rule be that it uses the first, if there's one overlap, you use the shortcut method, but otherwise you use for any deltas that have more than one square in their overlapping region, if you do the full check, you're always right, and if you do the short check for all the ones that are corners, I guess that's only 4 possible guys you would speed up. We could also special case like different positions, right, and get speed that way maybe, because we could do the 4 corners, get a special case, and then each edge gets a special, like if it's only overlapping with one edge, it gets a special case and stuff like that. Maybe could give us some speed. I'm not sure. Not sure. Another thing we could do is I have an idea. It'd be kind of interesting. I think we could speed this up. If we make the lookup table like the other one had, but use it in a smarter way, I think we could get the best of both worlds, where it's perfectly correct and doesn't do the sample times sample thing. I have an idea. Uh-oh, there's the problem. That should be a 1. 569. Let's see if that gives better... Whoops, what was that? Don't do that. See if that gives better behavior. Not really. Still broke. So, let's see, what else is going wrong here? Make sure it's actually built with the new changes. Take a quick peek. It's going to fill the whole thing out, and now it's going to start doing coexistence checks. The first one should fail because the value it gets is 0, and that is not the right one, right? The value of 1 is the good one on the 0, 0 position. So anything that has a 1 in the bottom right corner will work. So this one should work. This can coexist, right? That doesn't fail. That's going to keep going. Boop, that can coexist. It should get to the end of this without failing because perfect. Did cell 2 change? Yes, it did. So it pushes that change on. And then we continue up here. We get a new delta xy. Oh, uh-oh. Somebody changed the coexist table. Who wrote into the coexist table? Somebody did. When did that happen? Is it because of the change queue? My mem move changes plus n. Change count minus n. Somebody definitely moved something. Add change. I don't think that mem move triggered, but something interfered with my coexist table. Okay, right now the coexist table still looks good. And there's the problem right there. So how did that happen? Coexist tables. Do they happen to overlap with? Here it is. Yep. Well, let's just do you first. Alright, still failing, but now it's failing in a deeper location, which suggests that that's what I would expect to see if it was just the idea being bad. So it's like not aware that it can't do some of these things, and it tries to do them for a little too long. Yeah. Okay. So let me roll back all these changes then, because this wasn't quite the right way to do it. Okay, perfect. So, there we go. I'm going to reinstate a couple of these nice little changes. So scratch putter. I'm going to reinstate this change. I'm going to reinstate this change. Oh, I copied it at the wrong time. Okay, whatever. So just putter equals void pointer boundary. That's got an A in it, as I've since learned. Position, that should be position right there. That should be putter, yes. Position, boundary, boundary, minus the boundary. There we go. And scratch putter, if I come down here to the position part, yeah. Scratch putter equals round putter, scratch putter 4. Perfect. Okay, so that's good. And now, hey, I see this drunk Dane in the chat. I don't know how long ago that was. You messaged me like 5 minutes ago, it looks like. Hello. So, the idea, yes, the idea. So, this is a little bit intricate, and I want to get this out there because I won't remember it if I come back to this later without a video of it. So, here's the idea. The way they sped this up in the C# version was basically you have, actually let me go back to, whoops, let me go back to this, right? So the way they sped this up was they have basically a lookup table that says, alright, given that I'm on this cell here, right, I'm on this cell, no matter what cell that is, there's a dx dy to all the neighbors that I care about. So for instance, my dx of -2 dy of 0 gives me this neighbor. And then what I can do is make a table that says, alright, plug in a dx and a dy, and that gives you a subtable. And that subtable then you can plug in the sample, this sample here and that sample there, and that will tell you whether or not these two can coexist. Now the problem is that doesn't change the number of coexistence checks I have to do. It just is supposed to speed up a coexistence check. But the actual slowness of the coexistence checks is how many of them there are, not how long it takes to do them. The coexistence check itself is just 3 sort of cell checks. It's very cheap. The hard part is that I have to do like 4,000 of them every time I change one cell. So, yeah, quick diversion. Yeah, Mikkel, I've been working, I mean, I've not been working for 12 hours straight, but I've been working on this stream for a lot longer than I normally do, because I'm going late, since it's the last stream I'm doing for a while. So I'm producing a big, long stream, and then when I'm done, it'll be done for a while. So I've been going for about almost 4 hours. It'll be 4 hours soon. And I'm going to keep going, maybe to 6. I might take a break in about 15 minutes and then continue for another couple hours, or I don't know how long. Anyway, what I was saying was, so the nice thing that does is it does mean you don't have to do like these 3 cell checks, but the problem is the number of coexistence checks is still too high, and I want to get that down, because that's like the number of neighboring cells times the number of samples squared is kind of the time complexity of that operation, and that seems bad to me. But I think if I build this lookup table, I could then make an algorithm that does the number of neighbors times the number of samples. And the way I could do it is, I'm thinking, looking at any particular dx dy, right? So I've picked the cell that I'm looking at, and I go, all right, my original plan was pre-process that one cell, and then do all the dx dys for each dx dy, find the overlapping region, check that, but it turns out that that isn't good enough. That leads to too much sloppiness, and you get contradictions in your answers, right? So there we go. I don't have contradictions anymore, but I still have the problem that it's too slow. So, and you can see I have just gigantic numbers of coexistence checks happening right here. And so getting that number down is my goal. And I'm thinking, instead of for every sample this has and every sample that has, what I could do is do the pre-processing, but do it after I know my dx dy, right? So I know the cell position, I know the dx dy. I haven't started iterating over every possible combination of samples from both cells yet. So what I do is I know that this is where I'm going to go, and then I do a pre-processing step. And that pre-processing step iterates over all the cells of this sample, or all the possible samples for this cell, and then I iterate. Once I've done the pre-processing, I have a data structure that's not too big, and I iterate over all the samples of this cell and see which ones I have to eliminate. So, and yeah, Mikkel, once after this stream, I'm not going to be streaming for a while. My live streams will be gone, and I'll be recording. My Wednesdaily videos will be recorded and put up, but they won't be live. At least for a few months until I get around to getting internet, or until I find a new setup where I can stream from. But anyway, so the idea I'm having is do the pre-processing once I've decided what dx dy I have, then do the pre-processing. That means I have to do one pre-processing stage. Instead of per change, I do one pre-processing stage per neighbor of a change. That's still much smaller than the number of coexist checks that I do right now. And what I can do is the pre-processing here looks through the lookup table. So I don't have to do the long-form coexistence check for every pair, but what I'll do instead is say, my lookup table will say, all right, for -2, 0, look at every sample available to this cell here, right? And what we'll have is we'll create a table that'll be like this. We're saying, all right, I want to know which samples are going to be possible at this location here. So I create a table. I initially fill it with, I don't know, zeros or ones. I'll have to think about which one, but I fill it with zeros probably, because that's the thing that's easy to fill with. Alright. So these are all, suppose they're all the possible samples that that cell could have, or that any cell could have, and I fill it all with zeros. Then what I do is I say, alright, go to my lookup table where I have the dx equals -2, dy equals 0 subtable. In that table, what I'll store is for each sample that T1 could have, that the center cell could have, I look at, all right, here's one of the samples of this cell, and I give it that sample into that table, and what the table returns to me isn't another subtable. Rather, it's a list of all the possible samples that are allowed to overlap at that position. Right? And so what I then do is I go, okay, iterate all those and fill those with ones, right? So maybe all of a sudden that sample allows ones here, 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 and here, right? And so there's 4 samples show up that way. And I go, all right, well, there's still zeros in the table. So iterate, go to the next sample and see which ones it allows. And it's like, all right, well, this one allows maybe the same locations or something, right? And eventually you're done filling it. Now we can keep track of I think we can keep track of, well, even if we can't keep track of it, we can at the end say, no, I know how, we could keep track of it, or we could, maybe it's easier just at the end say, check all of them. If it's all ones, you're done. But you could also just say, don't check it, and then loop through all of the samples that this cell thinks it could possibly have. If you see a 0 at any of those positions, kill it. Now, I'm not sure that that's actually going to be faster, because now that I think about it, I still have to do probably a sample squared amount of work to look at all the samples of the greens of the center spot here, and for each one of those, fill out these ones. The number of ones I fill out could be up to the number of samples for each one that I put down. So let me think about that a little more. An or. Oh, it's an or. If the amount of preprocessing I have to do is samples squared, it doesn't matter. It doesn't help, I mean. Ouch. Um, hmm. Because what I could do is I could keep the original type of lookup table, which is all ones and zeros. It's not lists of numbers, but it's a four-dimensional lookup table. And then I use the first three dimensions, which are the dx, the dy, and one of the sample values here, right, to give me a table that looks kind of like this. And then I take all those tables that are um, uh, relevant to this, and I OR them together. But that, I think, would just be, the total amount of work there would just be the same as if I had uh, just gone through all the cells of that at dx dy then, because ORing two of these tables together is takes an amount of work equal to the number of samples, right? So that's not necessarily um, superb. Um, Hmm. I could do something higher level. Maybe. Which is, I might not be able to um, make it faster given, like, once I'm at this pair and this pair, right? Like, once I've determined um, the dx dy, I thought maybe I could determine the dx dy and then pre-process. And I also tried pre-processing. Maybe I didn't spend enough time trying to pre-process before the iteration. Is there anything else I could do there? I could look across all the existing samples and say, for each of these existing samples, store a table that says, all right, if sample 1 occurs here, then now there's too many samples or anything too big per sample. I was going to say, like, have a thing that maps out the entire surrounding region simultaneously. So, like, sample 1 would have a 25 by 25 thing where the center spot doesn't matter, but all these surrounding spots have some piece of information that's useful. But I don't know what that useful piece of information would be. I mean, I could do a few possible things here. Like, for instance, the square that goes right here overlaps with the square, the central one, a lot. And there are a few that do that, right? There's that one. Whoops, there's also oh shit, what is this? Undo doesn't appear, or redo doesn't appear to work in the version I've got. But, anyway, if that's the middle, I could look at one of these ones that overlaps by a lot. And I could say, look, there's only a few possible samples that can show up here. So let's handle that first. And when it's done, or not first, let's make sure to think about this in terms of this square here only has a few possible values. So we're going to have to probably, if we make a change on this cell, which is likely, then we'll have to make a change on this cell, which means we're going to end up having to consider changes here for both here and here, right? In other words, what I'm thinking is, whenever I make a change, what I'm trying to do, oh shit, what I'm trying to do is conform the entire grid to only take on values that are still possible given that change. I don't want to assume any information that isn't there, but I also want it to automatically remove anything that is impossible to become true. So what I could do is say, alright, upon this cell showing up, oh, if I make a special kind of propagation rule for when this has one particular value, I can then say, alright, here's the list of values that can show up here. Here's the list of values that can show up. Yeah, and do like a complete, So then what we could do is say, all right, when that became, there's only one possible value here, we then had an immediate surroundings propagation that was faster than usual because we have an optimization table that says, all right, when there's only one thing left at this spot, like if I'm processing a change for this spot and there's only one thing left, we have a deeper thing that does more stuff all at once. Because what really normally happens is we make a change here, and then we make a change here. And that change here is just saying like, all right, well here are all the possible samples that can go here given that change, right? And we also make a change here. Let me pick a different color. We also make a similar change here, right? So now this guy is also changed because of the green spot. But then one of these two processes their change first, and in doing so changes this guy again. So then this one here finally processes and potentially forces him to process again. What we could do is say, all right, if we know that there's only one, if what we want to do is simultaneously change all of these so that they use all the information possible. I don't want this to pass back and forth between each other. And the way I could do that is to say, if there's only one possible value here, let's have a pre-computed table that knows how all of these things have to line up, right? Like sort of a pre-computed propagation pattern for that particular case, because it's a common case that we're trying to derive to that. Anyway, every time we do an observation, that's the first kind of thing we have. That could save on a lot of the propagation time. And all it would take is up front doing a pseudo propagation and making a table that gives you some rules about how to eliminate a bunch of stuff right up front. In fact, that could be my entire goal, is to short circuit a lot of these things and eliminate them more quickly. Yeah. So in other words, rather than trying to pre-process anything, or rather than starting from the point of let's try to pre-process, I could think about these in terms of, once I fix this, like here I have a dy of -1, dx of 0. Once I've gotten there, what if I had ways of quickly saying, all right, like we don't need to check any of these samples because we know they're good or we know they're not good, and short circuit them because I have tables that let me do that somehow. Yeah. I wish I could pre-process this before doing the dx dy thing, because that seems like the right time to do a pre-processing stage on the samples available here. So for instance, if there's one sample available here, you have like we were just discussing, a table where I just know what everything, how to everything surrounding that spot should look immediately. So that I can just post all the changes where they are appropriate immediately. Another thing is once this is fixed, right, like even if this changes, that can't propagate down here anymore. So what I should have is a table that lets me see where have I already got established values that kind of serve as propagation walls, right? Like this spot, whoops, I'm sliding away. Technically, this spot here ought to propagate through to this spot here because they share a spot. But just because this changed doesn't mean that this particular cell changed. So maybe what I want to do is have some way of categorizing which portions changed, but that's a little tricky, right? I mean, certainly after one way to do it though is to say we have the full output grid and we have certain spots that we know are established. So after I've done an observation and I've done all the propagation, I can look at where do I have established spots where there's only one possible value that can show up here, only one possible value can show up here, and I mark all those established spots. And now I never propagate things that only have overlaps in established spots. So for instance, this whole area is established, and if I'm going through my propagation phase and I change this later, I change that, I could say, well, look, I don't need to do a change test on, like this should already know about that information, right? Like since we've said that, and we've done the propagation before we marked all that information down, we assume this cell already knows about this. This cell already knows about all this. This cell down here already knows about all this change too. So, like for instance, this one, right? So this spot here doesn't necessarily need to communicate with that spot there anymore, because even if it makes a decision, it's only changing these regions, right? Similarly, if this guy up here makes a decision, it's only making a decision that alters these spots, which don't overlap with him. Now, I'm not sure how we would do that quickly. Like, you'd have to very efficiently say, make a map of, we normally assume that when we make a change, that the samples that that the cells that got changed are the 3x3 surrounding area. So here through here, here, and here. We assume all that got changed. But what we could do is say, alright, assume all that got changed. Assuming all of this got changed, we need to make, we need to sweep the area around that square with a square. Alright, so like all those, all those, all those. And then what we can do is later say, alright, well, suppose only these things changed. Then the area you need to test is not including any of the things. so there's a finite number of spots that could change when I fix that, right? Um, if this one, if this one here got changed, then this is the set that is affected. I could make basically a table that says, alright, suppose this is the only one that got affected. Well, then the spots I care about don't care about anything there. I care about this one, this one, this one, this one, this one, this one, and this one. I make this table at the beginning, and it's just saying, given that position 2, 3 was the only one that got an update to its information, um, go ahead and only propagate to these guys here. And the reason we know that's the only one that got an update to its information is because we're keeping track, and actually all the other squares here were already settled, but this one was somehow not settled, right? And that might be unlikely for this particular configuration to happen, but basically what you're doing is you're asking a quick question, which is, by the way, does this also propagate to Okay, well, for one thing, I can do is I can stop testing this guy against himself. It's probably not worth much, but it's worth a little. What's up with that extraordinarily small generator time? That doesn't make any sense. What the hell is this? Why is that so much smaller than that? That can't be smaller than that, and the sum of those... Well, that is the sum of those, but how is coexist check so big, actually? Because these all look reasonable, but coexist check looks too big in that particular case. But also, why is that so small? That shouldn't be so small. Was it always that range? Something's broken with this timer. Coexist check. Why is that getting so much time? Is it because of the sheer number of times that happens that the count, that like the number gets off? Maybe. Really weird. See, that's too small to be possible, right? I don't understand. Okay, well, okay, this would be a way to check propagate to fewer spots, which would save a lot of time. That might be the way to go. And I think that this could be done. So we can easily make that table because as I'm thinking about it, I realize it's just a matter of doesn't even have to be a table. You just have sort of the 3 by 3 table here, or this table is the size of a sample that you mark down ones wherever you think a change has actually occurred. Like this is a spot that is actually up for change still. And then what you do is you find you look at that and go, all right, well, whenever I'm checking a position, I want to ask, is anyone in the sort of overlapping section of this position a 1? And you just check all of those. It's a quick check, and if there's no ones, you don't bother doing any testing on that particular spot because you're not going to find a change there. And then you can do a lot fewer coexist checks to find the ones that can actually be affected. Now the harder part is maybe finding that pink dot. So let me think about that. How do I, at the end of propagation phase, find all the spots that have an exact, definitely known single value that can't change? Well, suppose I have a grid. Doopy-doo, 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 doopy-doo. I randomly observe some location, so say I observe right here. Actually, it always observes at 0, 0 because their entropy, the noise on the entropy is so low that it doesn't seem to ever start anywhere but 0, 0. I'm going to think about how to fix that at some point in the future. But suppose it observes right there. So those will all be fixed by the end of propagation. Then it propagates information out. What it can then do is looking at, it could keep a list of which cells are finished, right? And anytime it looks through all the finished cells and says, all right, at the end of propagation, these were the cells that were finished. It fills in the block, there's the size of one sample from that finished cell and says, all right, this whole area here is now absolutely known to be finished and nothing else, right? And then it then empties that list, and then on the next propagation you get more things that are known to be completed, and again you fill those up. So maybe you get like, all right, well now this one is known to be completed, and so on. And maybe you learn that this one's known to be completed too, right? And then when you go and propagate on the next phase, you look at this table and you go, all right, well, to find the pink dots, I go, all right, suppose a change happened right here. Well, the pink dots are all the spots where an orange X doesn't line up. So my pink dots are these spots here. Right? So the way I would do that is fill this whole thing with ones, and then anywhere where the align, where shifting that in there puts that on an orange X, you would just iterate these spots and go, orange X 0, orange X 0, you're done. Right? And then or you could do it the other way, right? Put ones wherever there's a fix. So if that spot's fixed, that spot's fixed, everywhere else is 0. You then start doing the iteration across all the possible spots, and what you do is you ask, are any of the spots I overlap with unfixed? So, for instance, when you propagate this boy down to here, you'd look and go, oh look, this guy is already fixed. No need to look at that one, right? And that would be good. That would be good. Yes. Okay, so maybe that's a good idea. Um, I'd like to first try to get better readings on these numbers, if I can. Like, it's changing by a large order now. And I think before it used to have just 2 spaces there, and now it's sometimes getting down to 3, which is weird. Like that. Why is that so small? It adds up too. This plus this does kind of equal well, no. Sorry, this plus this does kind of equal this, roughly speaking. Now this is too big, which doesn't make any sense at all. I can't figure out what's going on there. Am I printing this the wrong way? Should I be using LLU? Is that the problem? Let's take a look. I see. Whoops. This is one of those darn things happening. Gotta get that working on the X pixel instead of on the character coordinates, because see, those don't line up in column number. Okay. So the problem I wanted to fix was these LUs everywhere. I feel like they might be wrong or something, because I'm getting dumb results. Hey, that's more like it. Alright, so I've been operating with a totally buggy thing this whole time, which means my run times were bogus, so I should just ditch them. Which means I don't even know if coefficients are faster than the feasible states. So I guess I should find that out first. Let's just git stash what we've got. No, let's keep it. Let's get I don't know what the head detached message means. Okay. Anyways, let me look at my Maybe I should open this up in a different... Alright, so I want to switch back and forth between these. So again, coefficients and feasible states. There we go. Okay, feasible states happen at 2AAA. Wait, no. That's the BA 05 2D5A 67. This happens at 7C0A1 DEEEE. Alright, so I'm going to stop the recording and start another video here. On the next video I'm going to test and see if the feasible state is actually faster, and then I'm going to try and mess with some other stuff. I want to try to see if I can do that optimization to do fewer checks, coexist checks, where we know that we don't need to. Okay, be right back.